Hi, welcome to the presentation. Part 2 of Solar Geoengineering is 14 times stronger than CO2 mitigation. In this part, we're going to look at IPCC CO2 estimates are too high using a simple model, and it'll help us understand the albedo decline on the planet and what is kind of missing from the AR6. Okay, there's a lot of good information here. We're going to use a very simple linear unsaturated model, and I'll talk about that. So this talk is based on this preprint, same as part one. So we're continuing. The my bio you can find over here. All right, in this part, we're going to use a linear unsaturated forcing model based on the natural climate system's Earth energy budget, using an energy method, so things add linearly. So let's look at that. It's very helpful. This is a paper that I wrote, and the reference is down here. So basically, the sun comes in with 340 watts per meter squared, and the sun goes right through the greenhouse gases and gets absorbed by the atmosphere and the Earth's surface, and comes out to about 238 watts per meter squared. Of that, we get some amplification effect or trapping by the greenhouse gases, which increase that flux about 61.8% to 147 watts per meter squared. So the total ends up being 385 watts per meter squared on the planet, and that comes close to the average temperature of the Earth. So we know it's approximately the correct amount of trapping, and the based on what is coming in and what is absorbed by the planet. I forgot to mention, of the 340, about 100 watts per meter squared gets reflected from the Earth's reflectivity, which is also called albedo. Okay, so now we have an understanding of what's going on, and that's all I really need to do. This is an iterative diagram, by the way, and the exact solution is 61.8 that I found in my paper. All right, so based on this, that's all we need to do for the simple model. All right, so we're going to use an unsaturated linear steady state physics-based model. Each unit of greenhouse gas has equal forcing potentials based on its spectral strength. So it's a linear amplification model, no feedback, designed to provide upper bounds. So it's a diagnostic tool, and it provides first order estimates. And it's based on the natural climate system, the pre-industrial one. I forgot to mention that this is a pre-industrial iterative diagram before we had forcing. So it's pretty much intact all the way close to 1950, roughly, but people usually talk about it as pre-industrial. All right, so now CO2, we're going to talk about a ULF model. It's an unsaturated linear forcing model. And we talked about 62%. I had 61.8% of the greenhouse gases uh, trapping. So this is an amplification effect. We could treat it that way. And the amount that is absorbed by the planet is the 238, and the trapping is 148, or amplification. So that 0.62 times the 238 gives us the 148 amplification added to the planet. So in general, the greenhouse gases consist of water vapor, clouds, CO2, and other greenhouse gases, and their percentage of that 61.8 is 50% water vapor, 25% clouds, and 19% CO2, and 7% other greenhouse gases. And that's basically all we need to know right now. So if we look at the 19% of the 62%, that gives us, if we take 19% times 148, which is the amplification amount or trapping, the greenhouse gases contribute about 28 watts per meter squared. So CO2 adds about 28 watts per meter squared to the natural greenhouse gas effect. So that would be a pre-industrial number. So now what we want to do is we're going to use a linear model, and we're going to say, okay, we have this number, it's 19% is the contribution, which is 28 watts per meter squared. And what was the pre-industrial amount of CO2 in the atmosphere? That was about 280 parts per million. Then for the linear model, we're going to use 2019 values, which was the time period numbers that the IPCC AR6 used. Okay, and that value was 410. So in a linear model, we would take the ratio, and so that we ratio that up. And so that increase in 2019 would be about 41 watts per meter squared total. So the increase from the pre-industrial means the CO2 added parts per million would increase the to about a total of 13 watts per meter squared relative to what it was in the natural system. So now we have an idea of the amount of CO2 and how that added parts per million converts to the total amount of CO2 added. So now we're going to look at that, and we're going to say, well, what contribution is that to the surface flux of the natural system? So in the natural system, we had 28 relative to the 238, which was the basic flux absorbed by the planet. So that's a scaling factor of 0.118. So again, this is a scaling factor for CO2 pre-industrial contribution of the 28 to the greenhouse gas relative to the absorbed amount. So now we take that scaling factor, we multiply that by the 13 additional watts per meter squared, and this gives us the perturbation, which is the forcing in the linear model. So this would be essentially an upper bound of CO2 forcing, which is 1.5 watts per meter squared. Okay, so now we have a number from the linear model. Let's look a little bit more in detail. Now, if I go through all the steps and I provide that into a general model, this is what I found. For example, if you take the 410 divided by the 280 and you put it in here, subtract it from the 1, and you use what's called the force, for the linear model, I call this like a forcing factor, as 3.3 watts per meter squared. So that would give you your 1.54 watts per meter squared. Now, this is a general model that is for all the greenhouse gases for an unsaturated linear forcing model for all the greenhouse gases. So this is the general model, linear model that works out. So if we go through all these steps that we just did, this is basically what would come out. All right, so let's look a little bit about the forcing model, the linear forcing model, and compare it to the general model that most people use, which is called a saturated model, given to mostly people use as estimates due to Meyer, who came out with this model in 1998. So this is the log model, and this is the linear model by comparison. Now the saturated model basically says that as we increase CO2, we will get less and less forcing increase as we add CO2. In other words, CO2 becomes a little less effective over as we add CO2 because it becomes what's called saturated. Now, one thing we can make a comparison about is a lot of people want to know what the forcing would be for 2 times CO2. Now, in the saturated model, if we take this ratio and make it a factor of 2, so 2 times CO2 would be, double this C0. So that would be, it would come out to 3.7 watts per meter squared. Now it's very simple in the linear model. You don't have to do much math because it's 2 minus 1. So that just gives us the forcing factor, which is 3.3 watts per meter squared. And this is supposedly an upper bound. So there's a discrepancy from the linear model, which is a diagnostic and should be an upper bound. So in general, people that use circulation models would be wise, I think would be helpful if they would look at these upper bounds from the linear model before they make attribution claims. It would be helpful. So this is a helpful estimate. It's a diagnostic model. It's not saying, well, the AR6 is not a good model. It's just basically helping as a diagnostic tool that we can use to provide estimates for upper bounds and understand the discrepancy. Now, so what we want to do is we want to see if the linear model has a reasonableness to it and why the discrepancies for upper bounds would be helpful. So these are the numbers that I get from the linear model. These are the upper bound estimates, and this is a comparison to the 2019 AR6 values. So we see that there's a discrepancy for the upper bounds. The actual overestimates by the AR6 is 29% for CO2 relative to the diagnostics upper bounds. Now, I should mention, why is this an upper bound? Because it's unsaturated model. So it's because the CO2, it's an upper bound as because it's unsaturated, it should give us the maximum values. So because we're using linear estimates. So now we have a 11% discrepancy for 2 times CO2 we talked about. We have methane, there's a 58% discrepancy. I got 0.228 forcing and 0.54 for the AR6 and so forth. So the total discrepancy, if you add just for these key greenhouse gases, we would get 2 watts per meter squared, where the AR6 would give you 3.3 watts per meter squared. So this is not the full story. If you go in, the AR6 predicts a lower number for the total forcing, but it's just the story for the key greenhouse gases. So we have about a 1.26 watts per meter squared discrepancy, and we'll see that this is actually a helpful number. And why is that? So because when we start talking about attributions, we'll see it provides room for what we are starting to observe, a planetary albedo decline. So that provides more room for that. So again, we had the 39% discrepancy overall, as I may not have pointed it out in my chart, but the value between the 2 and the 3.26 is a 39% discrepancy overall. And we have some discrepancy with the overestimate for CO2, about a 29%, and the doubling factor. So now, we have beginning to see that the linear model provides us with some very helpful information because we have more room now to attribute the albedo decline, which wasn't really taken into consideration in the AR6. So there wasn't a room for the albedo decline on the planet. Another thing that's helpful to notice is that in this model, I was able to come up with what's called the global warming potentials. So the global warming potentials is a number relative to CO2. So CO2 is a 1 factor in global warming potential, and relative to that, the model comes out with 78. The AR6 claims about 80. So we see that global warming potential is pretty much on target. So that's helpful and helps verify. Not quite as good for the N2O. That and the O3 ozone is not available for comparison. All right, so that's one thing that's helpful. Gives us some capability to say the linear model is doing its job. Another fact is that why would we want to use is it reasonable to use a linear model based on the natural system? Well, yes, it is, because in 2019, we had, between forcing and feedback at the time, we had a perturbation of about 5 watts per meter squared of forcing plus feedback. Out of the 386 watts per meter squared that the planet traps and also receives from the solar, it's only about a 1.2% discrepancy. So in a sense, we can say that at least 98% of the energy balance remains intact. So it's reasonable to use a linear model because the planet is very intact. The perturbation from the forcing is not relative. I mean, it's a big deal because it's causing warming on the planet. But in 2019, the perturbation was only 1.2% effect. So in terms of attribution, we can see that the divergence is helpful because what we're observing on the albedo decline is about greater than about 0.5% since 1998. So if we took just that number, we would see about a 1.7 watts per meter squared, uh, which is not in the AR6. So one would estimate this could actually be lower, but if we just did the basic physics kind of estimates, we would get 1.7. So the planet may not actually show that because of clouds and things like that, but general speaking, that's the albedo decline. All right, so in 2023, the imbalance, a lot of people are starting to write about that, and I cite many authors in my paper that have noticed the albedo decline and the fact that the AR6 discrepancies are having issues in terms of modeling. So we can see that the linear model would be helpful for that. Another thing is that we have increases of dark surfaces as we talked about in part one. So there's a lot of reasons for the albedo decline: cloud cover, aerosols, snow and ice melting. Also, urbanization doesn't help with the dark surfaces. So, in conclusion, the planetary albedo decline is overlooked factor, and the linear model helps explain where the overestimates are. And when you do these general circulation models, they do have to make attribution estimates, and so the linear model would be helpful in terms of that. In terms of governance, we have to address explicitly the albedo decline. So as in part one, I showed that solar geoengineering and solar forcing is a factor of 14 times more efficient or stronger than CO2 changes on an equivalent energy basis. So the Earth responds more strongly to short-wave reflection albedo than long-wave absorption. So that's telling us that we need to do something to stop that. And I had mentioned that we need to include this in the Paris Agreement, which is a living document, and we need to ban black surfaces, and we need to work really hard on the Arctic albedo decline. And so these kind of albedo targets need to be incorporated. So one thing that I do is recommend I wrote a paper called Annual Solar Geoengineering, and the pathways explicitly are provided in a number of my papers. And what that does is it recommends to go small, not big. Because a lot of people are concerned that if we go big, we'll have all these circulation problems and how the planet responds, and it'll cause a lot of destruction. So people are concerned about that, and the best answer, I believe, is the annual solar geoengineering method. So what we do is to stop. What it does is it says, well, let's just focus on stopping yearly increases for the global warming rather than try to do the whole thing at once. So we're not trying to reverse all of global warming, and it's about a factor of 50. For example, the perturbation in terms of temperature was 1 degree rise in 2019, roughly, and the estimate was close to a 0.02 temperature increase just for the yearly increase. Okay, and that's a factor of 50. Now that turns out to also be included in the energy imbalance, as well as if you're doing solar radiation modification, everything is reduced by a factor of 50. For example, if you're doing earth brightening, if we brighten the earth some with painting the things white, increasing the reflectivity, and we wanted to change just the 0.02, it would be 50 times less earth brightening that we would have to do. So the full thing, it's the most feasible option. It helps for political and governance. It's 50 times less solar radiation modification area. It leads to smaller annual solar geoengineering areas I just mentioned. It's better to go small than big, especially in the beginning, where right now we're able to afford that. And that gives us time to reduce the CO2 issues and also approach we need now to approach the albedo issue on par with CO2 because the planet actually responds stronger to albedo losses. So in a way, the albedo effect and the albedo is more urgent than even the CO2. So we need to look at these issues, the albedo preservation as well. Now, these are the mitigation approaches that I have in my paper. So we're going to do urbanization earth brightening would be required, hotspot earth brightening on the earth, so it's better to brighten hotspots. Space sun shading. Now, it's not 2 times the size of India. That number was poorly estimated by a number of authors. It's much lower if you wanted to do the whole thing, and it also, for the annual approach, is very palatable number. So you can look at that estimates in my paper, and also Arctic and Antarctic solar stratosphere, rather Antarctic stratosphere aerosol injection is recommended in those areas for the annual approach. Again, which is be a lot less effort, and people who write papers that are basing the issues in the Arctic and how stratosphere aerosol injection and all the methods that have been suggested are terrible ways, and we can't do that. They haven't looked at the annual approach, which is a lot safer. So all methods are important to achieve annual solar geoengineering. So that's it, I think, for our presentation. And I want to thank you for tuning in and listening to this method. Thank you very much.